Welcome back to LearnPiezo.org. Today we're continuing Project 1, Part E, which is going to be showing how to create loops with the functions we defined in our previous lecture, Part E2, in order to make automated measurements. So in this tutorial, we're going to loop the Python command line functions, and we're going to iterate over frequency, that's omega, and we're going to measure current, measure voltage, we're going to be measuring current, and we're going to be calculating impedance from these. So let's first now go into the experimental setup as you see here. We have, as we can see, our Picoscope. We have channel A, or channel 1. We have channel B here, and we have the arbitrary wave generator, which is our function generator, which is going to be supplying the signal that we're going to use to exercise this piezoelectric transducer here. Let me draw a schematic diagram how this voltage probe, and this BNC to alligator clip, how all of those are going to connect together. So this is the circuit. We have our arbitrary wave generator here, and it's going to go first into our piezoelectric transducer, which I'm drawing as a crystal. Then we have a resistor downstream, followed by ground. Let's go with channel A first. Channel A is going to be measuring the voltage from this point to ground. All of the probes have their ground at the ground of the terminal. The arbitrary wave generator, which will circle in red, is going to be connected here, which is sort of the same place, and it's going to end at ground again. The channel B is going to be measuring current by measuring the voltage over the resistor. So it's going to be measuring from here, and then its ground ground alligator clip is going to be hooked up to ground, which is defined by the arbitrary wave generator. So as you can see here, I outlined this in the schematic. So we have the red part, which is the arbitrary wave generator. We also have channel A, or channel 1 here being measured. Then we have a wire which is actually going to a resistor. So the wire here going to a resistor. This resistor is 325 ohms. We have then channel 2 measuring the resistance, measuring the voltage over that resistor, and we have here right there is the ground plug, or the ground clip of the arbitrary wave generator. So let's first set up Picoscope. So we have to measure certain properties. I mentioned you need to set up the Picoscope to make certain measurements in order for your desired measurement to come out correctly. So again, we're going to be measuring voltage, current in the form of voltage, and we're going to be computing the impedance, and we're going to be saving all of that to a CSV file. So here's the typical way that Picoscope loads. When Picoscope, you can actually load settings. For example, if I made all these measurements, enabled different channels, set the arbitrary wave generator, you can actually save those settings and reload them. So that will be what we're going to be doing in the future. Right now, we're going to be setting this to AC because we're not measuring any DC components. We have to turn that on. Also turn that to AC. We're going to turn the signal generator on, and we're going to be driving it with a sine wave at 1 volts. That's fine. So trigger, we're going to do a auto trigger, and we're just going to scale it something because the program is actually going to scale it. So we're just sort of drawing out what we want. And then we're going to make 2 types of measurements. Let's do measurement B first. If you measure the RMS voltage over channel B and channel B is the voltage over the resistor. It can give us the current. So that's one voltage we're going to do. That's one channel we're going to measure. So the other channel, the other thing we want to do is we want to measure the voltage, voltage over the transducer itself. I want to measure the voltage over the crystal itself. However, I can only measure the voltage here and the voltage here, so I have to subtract channel A. So let me write that in plain terms. Voltage the voltage over the transducer equals channel A minus channel B. You have to do that in the program. You can't use the RMS values because these voltages are actually time varying. They have an amplitude and they have a phase. And if you were just simply minus, the RMS of channel A minus the RMS of channel B, you're not accounting for the phase difference, which is actually very critical. So you have to subtract the actual waveforms, and that is best and most easily done in the program. So how do we do this? We have to set up a math channel. So channel A minus channel B, okay. And then we need to enable it. So it's enabled. You can't see it because it's sort of overlying. So you kind of see it like a little, just an extra scales here. You can kind of see that's going, that's there. So that's the voltage there. Okay, so now we need to add the second measurement, which will be here. Now this is the voltage over the transducer. And now we notice that the order of which I want these measurements to be made is A minus the voltage of the transducer should be first. So I sort of have to alter this. I'm just going to edit it, just change its order, because the order matters for the program's sake. So I just want to make sure that this is on the bottom. We're going to be using RMS. Hold trace. Okay, so now we have properly set up our function generator to make measurements. So now we're going to open, as we normally always do, we're going to open the Spider IDE development interface, and we're going to run that as administrator. I'm just going to pause this. Now it's going to run as administrator. I'm going to wait a couple of seconds, sometimes 10 to 15 to 30 seconds until it loads. So here's the program, and before I start, I'm just going to copy it. Actually, I'll copy it at the end into the PowerPoint file, so you'll have access to it. Hopefully, I'll also put it in the hopefully the description of so okay, as you can see, these are the same functions that I defined in the previous lecture, section E2. I defined the function get measurements, and it just gets two voltage values. I define the function signal generator, which I can change the signal generator values. I define the function time base, where I could change the time base appropriately according to the frequency, because there are only a certain values that the time base can equal in the picoscope. So choosing the appropriate one according to an index made by the available values is very important. If you want to alter that, you can change this n plus 1, n minus 1. In this case, I'm using n plus 1. Now we're actually going to start the looping sequence. Now you can see this is the only code I wrote. This code right here is the only code which is new. So it's not so much. I'm going to show you what's happening with it, and what kind of very interesting results we'll get when we run this code. So here we go. So first, I'm going to be using a different package for this, because before NumPy is the numerical sort of processing package of Python, and hence the term NumPy, and we typically import that as NP. Spider is already going to import that for you, but it's nice to have it explicit in case somebody else is using a different IDE or running the program straight from the Python console out of Spider. So we have to define very important parameters. They start with the frequency. So define. So I'm just going to comment as I go. Define frequency iteration values. So the start frequency I'm going to decide to be 10,000, and the end frequency I'm going to do as 50,000. Okay. The interval frequency I'm going to choose as 100. So I'm just defining variables that has sort of nothing that is going to go directly into the program. However, this is important here. Intervals. I need to find out how many intervals exist in between these two values according to the interval frequency. So so as we're going from 10,000, 10,100, 10,200, how many intervals exist? And I need to know that because I'm going to be using the linspace function of Python of NumPy in order to describe and fill in that array which we're going to iterate through to find the voltage and the current at the different values. So I found the interval using this formula. Because Python indexes from 0, I have to add 1 here in order for this to become a whole number instead of iterating through it. 999 values, I have to press 1, add 1 to it so then it can iterate through 100 values, for example. So that plus 1 is very important in order to get whole numbers from what you would normally expect to be whole naturally. Then I want to describe an important parameter called frequency space. So I'm just going to write here, I'm going to initialize arrays, data arrays. So how do we initialize these data arrays? First, we choose this frequency space. Now, frequency space is a array which we're not going to change. It uses the function linspace in order to create an index of variables or index of numbers starting from the start frequency to the end frequency with the appropriate intervals, number of intervals here, which I chose, and that will actually end up being the interval frequency in between these numbers. And these three, so initialize, I'll say frequency array, define frequency array, and here are all the values which I'm going to be sort of measuring and calculating for each frequency. It will be I'm going to define, or rather initialize, output measurements. So we're going to be measuring channel 1 voltage, which is actually going to be the voltage over the transducer. And this is actually, these numbers, or these start frequency and frequency intervals, I just want an array of the same length as this one. That's the whole point of using this exact same notation. You just want the same length. If you define them as equal, sometimes I've saw problems. For example, we could have defined channel 1 voltage equals frequency space. However, I saw some problems at one point, so I'd rather just define it fresh for each one of these parameters. And this is going to be the RMS voltage we're measuring. This is also RMS voltage, so you can divide that to get the absolute value of the impedance. So now we're going to take a look at the iterate and iterate over frequency. So now in this section of the code, we're going to iterate over frequency space and get measurements. So we start by a for loop. So we're going to integrate across the variable n, and n is going to range from 0 to the length of frequency space. So essentially, we're going to iterate through the entire variable, or the entire length. So first, what we do is we set the function generator. Here you can see I'm using 2 volts amplitude, and also the frequency space variable, which is going to match the index of the loop. Then I'm also going to change the time base to be appropriate, because we know as the frequency increases, the appropriate time base, or seconds per division, has to be changed in order to get a decent number of cycles. Here I am, so set the function generator, set the time base. Here I'm going to assign the measurement. So I'm going to take the measurement, and then I assign it to channel 1 voltage of the same index and channel 2 voltage of the same index. And then I define impedance by this. So I define impedance by its index and channel 1 voltage and its index divided by channel 2 voltage divided by 325, which is the value of the resistor. Now this resistor is not a non-inductive resistor. It will change its value with frequency, but this particular one, because it's a relatively low value of resistance, it's not going to change too much. So we're just going to assume for all practical purposes that it's going to remain at 325, just like it was using our multimeter in its measurement. Alright. So the next part we're going to be doing here is we're going to be saving the data. So we're going to get huge arrays with channel 1 voltage, channel 2 voltage, and impedance, and we already have our frequency space. So in this next part of the code, we are going to write the data to a CSV file. And this part, and this variable called head, I'm just defining the header of this CSV file. The first column is going to be called frequency, the second channel 2 voltage, third channel 3 voltage, and the fourth is going to be impedance. I'm going to save it as trial.csv, or I could just say 10 kilohertz to 50 kilohertz, and I'll write step 100 hertz, maybe something like that could give you a good description of what you're trying to do. So this is the function I'm going to use to save the text to that CSV file. I'm going to define the name of the CSV file, and the CSV file by default is going to be saved into the same folder as your Python function. So, or you could define the directory from the initial case. You can search more about how to define directories online, but you have to sort of use an opposite side slash in order to define that. So we go with the then we define our array, which is going to be used for storing the data. See, we have all of these variables: frequency space, channel 1 voltage, channel 2 voltage, channel and the impedance, which are all going to be linear arrays. It's not going to be in the form which is going to work with columns, so we have to take all of these variables, which are large arrays, and transpose them. And the next part, we're going to tell the program that we're using comma as a delimiter. So if you use a CSV file, it's going to open, and for the header of this, it's going to put this string variable head, so it's going to fill in quite nicely. And finally, we will just plot the impedance versus frequency using Python, and this is the code that we use to do that. It's very simple: frequency space impedance. There are a lot of different ways you can add labels, change the type of line, points instead of line, many different things, but we're just going to do the simple plot right here. Okay, so now I'm going to press play. It's going to, or not play, I'm going to run the program. Hopefully no errors. And we're taking a look at this. Now we see the frequency changing, and this is going to take a little while. I'm not going to wait through all of it. So I'm going to pause this recording, and we're going to come back when the program is finished. Okay, we finished now. So I am happy to change this back to 1 kilohertz. It's better not to leave it on a frequency where it's going to be drawing a lot of current. So just take it back to 1 kilohertz, a high impedance case, far away from any type of resonance activity. You'll be probably pretty good just leaving it like that. Or you can just set the amplitude to 1 or something. Okay. So, so you saw we iterated through all the frequencies. I just wanted to change this a little bit. We actually need to plot it in log format because the impedance values change over several orders of magnitude, the current levels, believe it or not, and it's due to the resonance anti-resonance effect due to mechanical resonance. So we're just going to highlight all of this, and I'm just going to run this, just this part. So as you see, we have impedance. We have impedance on this scale, and we have the frequency in hertz on here. You see the typical behavior of a capacitor is when you're increasing the frequency, the capacitance, or the the impedance is getting lower as the capacitance, as the frequency is getting higher, the impedance is getting lower, until you hit a sort of an anomalous region, which is known as a resonance region. Here we have a mechanical resonance, which occurs approximately almost exactly at 40 kilohertz, and then it rises after that, and it furthermore decreases here at another resonance, which is not the operating frequency. Typically when you're designing transducers, you design them such that these type of resonances, which aren't the main resonance of the system, meaning the lowest impedance point, are far away. We can see the impedance is about 20. However, this is in steps of 100. Whereas probably in order to get the true impedance and not to miss a value, we would probably need a step in the order of 10 to even 5 frequency intervals. But that wouldn't be possible for the large range we use. Because we're measuring the large range, we use a slightly larger frequency interval, which is about 100, which took a couple of minutes on this function generator. It's likely if you use the C commands and the DLL and perhaps some of the other Python modules for the Picoscope 2000, you'd be able to run this a lot faster. However, this approach I found is still simple and gives you a lot of valuable information. What's going on here is probably other resonances occurring, minor resonances. A lot of times when you actually, right now the transducer is sitting by itself, but its behavior significantly changes when you adhere it to your structure, which will be holding some type of solution and whatever you're going to clean inside of that solution. So when you actually attach it, it changes the boundary conditions, changes the resonance frequencies, all of them differently, including these parasitic, non-ideal modes, which are a byproduct of its having many resonance frequencies, and the main resonance, which is an extensional mode. We also saw that we did dig into we did save this as a text file, so I'm just going to dig that out real fast here. So we saw this is the file that we saved it to. I'm just going to see what it looked like. Okay, so this is it. We can I'll keep that pinned. We want to then try to let's map out this frequency. Well, let's do all of these together. Okay, we're going to plot all of them. We're just going to plot the lines. So let's just scroll down and see what this looks like. And we will decrease the size of this. What we're going to need to do is, first of all, we need to make sure that this is on logarithmic format. So we're going to change that to logarithmic. Again, I just I'm plotting all the voltage, the current, and the resonance frequency. Sorry, the voltage. I'm plotting the voltage. I'm plotting the current, and I'm plotting the impedance. So channel 1 voltage is blue, and I can actually use my pen to write all of this. So here we have the, I just copy pasted the diagram. So here we have the impedance. Which is basically the channel 1 divided by channel 2 divided by 325, which gives that the current. We see the impedance has, it's basically a ratio. Let's take a look at channel 1 voltage and understand what is going on with it. It's pretty constant out here, as you see. And then as we get to the resonance frequency, we see a large dip in the resonance, in the voltage. And why is this dip occurring? This dip is occurring because the arbitrary wave generator, it has an internal resistor. There's two reasons actually. The arbitrary wave generator has an internal resistor. I'll just draw it out here. This is the picoscope. And we have our crystal, and we have our grounded resistor. So one reason why that frequency drops is that at the resonance frequency, the current is the highest, obviously, right? And when the current's the highest, current has to pass through this internal resistor, or we call it output impedance, then voltage drops across this. So we don't get that full 2 volts. Versus when this is a very high impedance, this is relatively very low, so all the voltage drops over this transducer. Similarly, for the same reason, when we get to the resonance frequency, this 325 is a lot larger than the impedance of this crystal, or this transducer. So therefore, a lot of voltage drops over there. So we actually have a dip in voltage due to the dropping of voltage across the measurement resistor and the dropping of voltage across the output impedance of the function generator. And we also have another again here. So when the impedance is again lowest, we have the resonance frequency, and its highest is the anti-resonance. Now I can't exactly say why this is happening, why we have a little bit of noise here. It could actually be there. It could also have to do with other nonlinearities which exist in the system. But typically we would not have as many features there. But this is the second resonance, which is likely to be something which we would normally try to design out of our system. However, likely when we attach this to a external structure, this resonance frequency is going to be it's going to behave significantly differently, and we probably won't have this type of behavior around. Next, I want to show you the current. So as we are increasing our frequency, we're obviously increasing the current going through our piezo capacitor, which is our transducer. However, when we get to the resonance frequency, we see a peak in our current, after which it decreases significantly at the anti-resonance frequency. Anti-resonance frequency is a sort of parallel resonance between the clamped capacitance and the LCR branch, and I've already described this in other lectures. But basically this anti-resonance effect where the current coming out of each of these sides cancels, the current cancels and makes it 0 or very close to 0. Therefore, the impedance is very high and the current is very low. One thing what you may not have expected is how come this current, the orange, how come this current doesn't like peak up like that? The reason the current doesn't peak up is because of the series resistance and the output impedance. When the current starts increasing, basically the voltage across the transducer starts decreasing because the voltage starts dropping over these parameters. So it sort of self-balances itself out. It self-balances itself. Well, that's called self-balancing. It balances itself, therefore the current is sort of maintained informally. However, if we instituted a closed loop control where we actively control the voltage such that the voltage over the transducer was constant, we would indeed see a very sharp peak at the resonance frequency. However, since the voltage was not actively controlled, the system was allowed to do with the voltage as it pleased. We don't see a peak in current, and the voltage is the one that spikes lower due to its dropping over the the output impedance, and also especially the series resistance. So here we've determined very important properties. We can get the resonance frequency. We can also perform, again, we can change these parameters. The resonance frequency approximately, so you can change it to about so let's actually go into our scale, and we can format the axis, and I sort of want to go to 39,000 to 41,000 hertz. So okay, that's good. So here we have the the frequency here. So we can sort of understand the the resonance frequency was about 12, but this is about 15 or so. Actually, let's take a look. So it occurs about, where does it occur? The resonance frequency occurs approximately at 40.01 kilohertz, and it's at 22.6 ohms. Now, if we want to get a better understanding of that resonance frequency, we would change this to, let's say, 39, and let's say 40, 41, and we would decrease this to 10. And we would see a lot better resolution and better able to understand what the exact impedance is. But this gives us, nonetheless, a very good estimation and understanding what that resonance looks like. So, what else can we discuss? So there's a lot better way to gather more data. So it's better to get the exact resonance frequency instead of sort of toying around with the arbitrary wave generator frequency and looking at voltage and current, separately, manually. Because we did all of this with the understanding that with the automation, we have a lot more data, and it's more accurate, and it presents itself in nice, graphs and images you can put on PowerPoints and slides to explain the behavior. This is something that a $10,000 impedance analyzer also does for you. It's going to be more accurate. It's, I went through the whole. It's going to have a larger frequency bandwidth it could easily tolerate, but that level of accuracy is not necessarily needed, because when you really go into the practical devices, you don't get this type of value. So as soon as I'm going to adhere this to a structure, it's going to have a different behavior, and the exact characterization in this case, I don't believe it's that as necessary as to use the same tool to be able to tell the difference in behavior. So basically what I'm trying to say is that this is extremely useful. It may not give you the exact an answer as accurate as an impedance analyzer, but I believe it can be reliable as one. And especially since you have full control, you can do this loop. However, you can do a controlled loop. You have a lot more power and a lot more perhaps data points as well, because you can define a smaller frequency interval. You have a very powerful ability to gather data in a way that you deem is good. So I'm going to finish this lecture by just copying all this code. And I'm just going to paste it into the last slide for anyone who wants to look at that later. So let's just make it a different color. Let's make it red so everyone can see it. So just to go over what we did in this lecture, we first went over, why we need to loop. I discussed, and that's basically automation. The second point is, how do we do that in Python? Or any other programming language. that you want. The same, basically the same idea, and you know, be understood. You know, voltage, current, it's lagging on me, and impedance. And we measured the impedance firsthand, and it looked like this, more or less. We have this type of behavior. We have a capacitance. We have a capacitor-like behavior. Here we have a LCR circuit right there. And then here, at this anti-resonance points, we have a parallel resonance between the capacitor and the LCR. It sort of cancels out. That this is the actual working resonance. And we have other types of behavior going on as well, because this is a mechanical system with many resonance modes, one of which is important to us, the others of which we try to avoid. So I hope I went over this with clarity. Please email me. The contact information and the rest of the PowerPoint are on my website, Learn within R Piezo .org. Thanks for watching.